In this video, we will be solving a problem based on latent of heat. This problem is problem 7 located on page 94, section 4.2, and this is practice for C. Alright? Okay. Let us proceed. Problem 7. An ice block of mass 2.5 kilograms and temperature 0 degrees Celsius slides with an initial speed of 5.7 meters per second along a horizontal and straight ground. So let us draw a picture of this problem on this piece of information. Suppose we have a straight ground here and we have a block of ice. It has a mass m. Mass is 2.5 kilograms and it moves with a speed v initial or v ice, which is 5.7 meters per second, and it has a initial temperature Ti, which is just 0.0 degrees Celsius. Now the problem says if 3.3 times 10 to the power of 5 joules of energy are needed to melt 1.0 kilogram of ice, what is the mass of the melted ice, assuming that all the initial kinetic energy of the ice is transferred into internal energy? So basically we are interested in how much of Ke produces heat, because this heat or this energy flow will increase the internal energy. Since the problem says that assume that all the initial kinetic energy of the ice is transferred into internal energy, then that means we are interested to find how much of this kinetic energy produces that much of heat, such that this heat increases the internal energy by that much. Okay. Remember, this Q, this heat, will increase the internal energy of the ice. We are interested how much of that. Now, indirectly, we are given the latent heat of fusion, LF. In that case, it is 3.3 times 10 to the power of 5 joules per kilogram. So what I did was this. We know the latent heat equation, or latent heat of fusion equation, is Q equals to plus or minus mLF. Since we are melting, we are interested to find the amount of melted ice. We omit the negative sign. We just want the positive sign because we are adding heat to the system, to the ice. Now, we have given Q, which is 3.3 times 10 to the power of 5, and the mass of 1 kilogram. So if we divide both sides by m, we get LF is equals to Q divided by m. And if you divide 3.3 times 10 to the power of 5 joules by 1.0 kilograms, you get exactly this. So basically, we have given, the problem gave us the latent heat of fusion, but indirectly, alright? So, we have now the latent heat of fusion. And physically, this happens because there's friction. See, as the mass, or as the block moves to right-hand side, suppose, the friction between the ground, the surface, between the contact surface of the block and the ground will make friction. So there's a friction force. And this friction force, what does it do? It will vibrate the molecules. The molecules inside the block will vibrate. Why is that? Because as the friction happens, energy will flow. In other words, heat, energy in transit from the ground. It goes into or inside the system, inside the molecules of the block of ice. And thus, as a result, there will be a temperature difference or temperature rise. So all of this cause is by friction. Friction will add heat to the system. The heat will flow into the ice, vibrate the molecules, and then breaks the bonds to change the phase. But for this problem, we're interested how much of that kinetic energy melts the ice. So we are looking for a partial phase change, not full phase change, because it requires a great or huge amount of energy just to melt all of this ice, all of this 2.5 kilogram ice. Okay, we are not interested in that. We are interested how much of this kinetic energy actually produces the heat to get that partial mass of this melted ice. So that's why we use the equation kinetic energy is equal to Q. That means we are interested to find how much of this kinetic energy is converted to heat. Well, we know that kinetic energy in that case is 1 over 2 m of the ice, v of the ice squared is equals to, now what kind of equation should we use for Q? We are interested for melted ice. So we are going to use which equation? What do you think? Specific heat capacity equation or latent heat of fusion equation? Of course, we use the latent heat fusion of equation. I mean the latent heat of fusion equation. In that case, it is m melted and then multiply by LF. Okay, we are interested to that. We want to find how much of residue is there, because notice that after some time there will be a residue here, a residue of melted ice, and the ice will perhaps comes to here. This is the block of ice. After some time, then it will left or leave amount of melted ice. There will be a leftover of melted ice. So what do? We solve for the melted mass. So m melted is equals to mass of the ice, initial velocity of the ice squared divided by 2 times of LF. Now this is, in that case, is just a substitution problem. We just substitute the values and we obtain it. So we have mass of the ice, which is 2.5 kilograms, multiplied by the initial velocity squared, 5.7 meters per second squared, divided by 2 times of that latent heat of fusion equation. I mean, just the latent heat of fusion, 3.3 times 10 to the power of 5 joules per kilogram. Okay, so we get the melted mass that is roughly or approximately is about 0.123 grams. Okay, you should get about something like about this. Of course, as you solve it, you get in kilograms. You have to multiply it by 1000, all right, to make it in gram scale. And that is the amount of melted ice. This is the partial phase change. This is the residue. This is basically the mass of this residue, this melted ice. And that's it for this problem. Thanks for watching.